Wanted to give you the notes for section 3.1. I'm talking about functions. It's introduction to functions. Um, First thing it says, what is a function? So a function is a relation in which each possible input value leads to exactly one output value. Um, Sometimes you'll see text describe it as the phrase in which each x value, which we're going to use as our input, is paired with one and only one y value, which, using the terms from the above definition, would be considered our output. I'll talk about this graphically here in a little bit, but there are several different ways that we could talk about representations of a function, meaning that you might see them in a table or sometimes a tabular form. You're going to see graphical, and this is probably the easiest way to determine if a relation is a function or not. I'm going to talk about that here in a little bit. We have what we call mappings. I think some textbooks might call them arrow diagrams. I'll show you what one of those here is in a moment. Or a list of ordered pairs. Off the top of my head, those are the different ways you might see a representation of a function, showing the table in really a tabular form and a list of ordered pairs. Those are kind of the same. And if you think about it, a graphical way is also the same. It's a graph is simply a list of ordered pairs. It just gives you a lot more than it usually gives you an infinite set of ordered pairs. Not always, but a lot of times it does. But it's still a collection of input and output values, much like a list is or a table is. A mapping usually looks something like this. Usually they take like a set of objects, so let's just call this set A. And in that set we might have our x values, so or input values. So we say maybe, and they could be anything. Obviously, it's nice to use values or numbers for us. So let's say I put 1, 2, 3, and 4 in. And they should then be paired up with some set B. Okay, so these were our input. These are our output. And they say, well, 1 can be paired with something, so that input. Now here it says each input is paired with one and only one y value. So that 1 can only go to one number over here. So maybe it gets paired up with 5. Okay. This 2 then might get paired up with some other number, let's say 6. This 3 might get paired up with some number 12. And then this here gets paired up with maybe 20. Okay, so that would be considered a mapping, and we see here that each x value, each input, is paired with one and only one output. So this is a function, and meets that definition. Another, I guess, kind of going back, and we'll continue talking about this in a moment, but another way that we can see representations of functions is through an algebraic rule, okay, which would be some rule, maybe some equation that takes this 1 and transforms it into a 5. And then we apply the exact same rule, and it takes a 2 and it transforms it to a 6. And we apply the exact same rule to 3 and it transforms it into 12. if at any point, so that is considered a function. That's kind of the most basic way of seeing it. Now, we could actually have something like this where instead of that 2 getting paired with the 6, so let's say the 6 wasn't in there, that 2 could be paired with a 5 as well. Okay, because it's saying that your input, each input has exactly one and only one y value. Well, 2 has only one y value, it has a 5. Even though 1 has a 5 as well, 1 has only one output. Okay, what ends up being a problem? So these are functions. Okay, so you can have multiple inputs pointing to the same output. But what you can't have is maybe something like this. Let's say I've got my inputs here of A, my outputs of B. Let's say A is 1 and 2. And let's say that we've got objects 3 and 4 over here. You can't have 1 going to 3 and then 1 also going to 4. Okay, regardless of where 2 goes, 2 could go to 3 or 2 could go to 4 or whatever. But you can't have a situation where you have an input. This here is saying you have an input of 1, and now it has 2 outputs or 2 y values. And that violates this idea here, or that idea there that says it leads to exactly 1 output. This input leads to 2 outputs. So that's a problem. Okay, and that is going to make maybe more sense when we start talking about what we call the vertical line test here in a little bit. So that's the way we usually generally speak about mappings. Tabular form is going to be very similar to this. Let's say I put this thing here. Let me scroll down. I guess I can't. I could take this information here that we have for this mapping and I could put it in a table, and I could say my set A and my set B, or my inputs and my outputs. I have 1, 2, 3, and 4 as my inputs, and 1 is paired with 5 as an output. We have 2 paired with 5 as an output. 3 goes to 12, and then 4 goes to 20. So we're going to do that. Okay, so that would be the tabular form. The list of ordered pairs, well, that's nice, because once it's in tabular form here, it's just 1, 5. Go straight across, 1 and 5, 2 and 5. So inputs, and these are outputs. We have 312, and then we have 420. Okay, and then I could, if those are ordered pairs now, if that's the way we're going to view those, we could put those into a graph and we could plot them as ordered pairs. And that would be another way of viewing that relation or function. Moving down to this idea here, function notation. Basically what we have a lot of times is that we have y is equal to some rule here, whatever that rule may be. Okay, and there's basically equations that we've dealt with. Maybe they're linear, nonlinear, whatever we've graphed. Some of those things that we've graphed maybe in the past have been functions, and some of them have not been functions. As we move through this course, it's going to be nice and useful to, before we do anything, to look at the problem that's being provided. And if there's a certain notation in there, that notation may provide you insight on whether the graph of what you're looking at is a function or not. And the way we do that is we write essentially y is equal to f of x. Okay, f is just the function, and then this x here is the input variable that we're going to be dealing with. Okay, so just some, just a general, like, let's say I deal with x squared. So we know what y equals x squared looks like. Okay, it's the general parabola starting at vertex is 0, 0. We have the point 1, 1 on there. We have 2, 4. We'll have negative 1, 1. We'll have negative 2, 4, and so forth. And those points are going to go on forever. Okay, make those points bigger so we can intersect. But this thing actually ends up being a function, and we'll talk about why here in a minute. But if we think about every x value that you choose off of here, it gets paired with only one y value. So this thing is a function. So instead of writing as y equals x squared, a lot of textbooks and authors will say it's better to write this as f of x. So y is equal to f of x. So to replace that is equal to x squared now. Because when I see this, we can view it still as y. So f of x is your output value. So that expression there is referring to your output number that you're getting. The x here is your input number that you are plugging in. But this is saying that this rule is a function, meaning, because of this notation, because we're using f of x, it means that we already know that for any x value that I plug in, I'm only going to get one y value back. So for instance, if I take something like f of my input value is 2, okay, 4x squared. So what this means is everywhere I see an x, I'm going to replace it with that 2. So over here I see x squared, so I'm going to replace it with 2 squared. And that gives me 4. Okay? So what we're saying is that with an input of 2, we get an output of 4. Because it's a function, I can put that 2 in endless amount of times. And every single time I put that 2 in, I'm going to get that 4, so that same exact 4 back. I'll never get another number back. Where in some rules, some equations, that doesn't always happen. But if that's the information, now I put 2 in, I got 4 back. We'll put 2 in as an input. You got 4 back as an output. We write this as an ordered pair. It's x comma y. Okay, y being the vertical distance from the x-axis. But sometimes if we go off of this idea here, y is the same thing. If it's a function, y is the same thing as that notation, f of x. So sometimes we'll see ordered pairs. If it's a function, we'll see ordered pairs written this way, with x comma f of x. Okay, and then f, the reason we use f obviously stands for function, but we can use h. So we have h of x is equal to some rule. A lot of times they use g. So it doesn't really matter what letter you use, but g is the function, h is the function, f is the function. So that's kind of what we're talking about there with function notation. When we get down to these examples here, what they're asking for is, and this is the tabular form right here. So these x values are your input, okay, and these values down here are your output. So what they're asking, essentially, what they're telling you here, is that if I choose x to be 0, then f evaluated at 0, so f with 0 plugged into it, is going to kick back to me, whatever my rule is, it's going to kick back a 1. This is saying if f is evaluated at -2, it's going to kick back a 5. This is saying if f is evaluated at -4, it kicks back an output of 10. This is f of -6, and this is f of -8. So that's what this table is telling us, and you see similar tables to this all the time. But if they want what is f of -4, well, that means the input was -4, so we're looking at this -4. What's the output you get? You get 10. Okay. Here it's saying what's f of 0? Well, f of 0, the input was 0. Plug that into this rule, whatever this rule might be, and it's going to kick back this 1. All right. Now we can do, f of, we can sum these things together. We can do f of -2. So this is called a combination of functions. So we can, find f of -2, which f of -2 gives us output of 5. And we have our plus sign, which is that one right there. And then f of -8, well, f of -8 is going to produce us 20. So we get 25. So we can add these rules together to get a total. We can subtract them, we can multiply them, we can divide them, we can do all the operations that we've ever done with anything else. Because essentially what we're doing is we're doing addition, subtraction, multiplication, or division with output values, with numerical quantities, and we can do that. The next one says f of 3. Well, if I look at this rule, okay, these x values that we're plugging in,
3 is not one of the inputs. Okay, so for this one, we basically say that our output does not exist. Okay, there is no output for that 3. Coming down here now instead of giving you the specific outputs that came from specific inputs, now they're giving you rules that would allow you to generate that maybe table on your own. So what this is saying is that now we have f of x is equal to the square root of x and then plus 1, and that plus 1's on the outside of the radical. So here where it says find f of 4, what that means is find f, x now becomes 4. So everywhere in my rule over here, where I see that value right there, it's an x in the rule, it's an x over here, but now when I evaluate with 4, everywhere I saw the x, these two things kind of mean the same thing. The x has become a 4. So over here, the x needs to become a 4. And then I got my plus 1. And now I evaluate that. Square root of 4 is 2, plus 1 is 3. So f of 4 right now is 3. They then want us to find g of negative 2. Well, g of x is this negative x squared plus 2. All right, so now I'll plug in g of negative 2. That's what they're asking for here, so I plug negative 2 in for x. So now over here, I plug in my negative 2 for x, and I want to add 2 to that. Okay. Now the thing is that this exponent here, this 2, it goes to only the object that is directly in front or behind of, and it's directly behind the x. Okay, it's not directly behind the negative, so I'm not going to square that negative. But when I use an input that's negative, okay, I will be squaring that negative there from my negative 2. So when I evaluate this, negative 2 squared is 4, but we've got the opposite of that 4. So it's going to be opposite 4 plus 2, which gives me negative 2. So g of negative 2 is negative 2. What this thing is asking me to do is, can I subtract these things? Can I take 3 minus this? So 3 minus negative 2 actually turns into 3 plus 2, so we can evaluate that thing at 5. We'll do similar things for part B here. It says find g of 3 plus then 2 times f of 1. So I find the g rule, and we'll plug 3 in. So g of 3, so now this x becomes 3. Okay, now again the power is only applied to the object that it's directly behind, so it's directly behind the x and not the negative. So when I square the 3, that's all I'm squaring. So I get that symbol, the opposite, square that, I get 9, and then plus 2, so it gives me negative 7. So g of 3 is negative 7. I'm going to add to that. Now it says 2 times f of 1. We want to evaluate f of 1 first, so we'll take f of x, which was root x plus 1, and evaluate that now at 1. So root x becomes root 1 plus 1. Well, square root of 1 is 1 plus 1. This becomes 2. So f of 1 is 2. So this 2 times, now f of 1 was 2. So now we can evaluate. Negative 7 plus 4 gives me negative 3. Okay. Working through option C here, we've got the opposite of f of 64. Okay. Well, let's find f of 64 first, and then we'll deal with the opposite of that. So f of x, again, is the rule square root of x plus 1. Well, now our input, our x value is 64, so we'll take square root of 64 plus 1. Well, square root of 64 is 8. 8 plus 1 gives us 9. So f of 64 was 9. If I take this opposite here, opposite of that would be negative 9. Plus then I want to evaluate g of 2. Okay, well, g of 2. Okay, so our g of x rule is opposite of x squared plus 2. I want to evaluate at x being 2. So I will put negative in. I'll put my 2 in. I'll square that. And then add 2. So 2 squared is 4. We get the opposite of 4 plus 2. So it ends up giving me negative 2. So we get negative 9 plus negative 2 gives me negative 11. And the last one is a little bit more kind of cryptic. It's now inputting algebraic values, expressions. So when I want to find f of b, let's actually write the f of x rule first. F of x says root x plus 1. But now my input becomes b. So all this changes to is wherever I see an x, it now becomes b. So root b plus 1 is what we're looking for right there. Okay. The next part says g of a plus 1. Well, g of x was the opposite of x squared plus 2. Now, that x, that input, is a quantity. So I'm going to have this negative, and then my a plus 1 squared plus 2. Now, if I have a plus 1 squared, that means a squared plus 2a plus 1. And now you have the opposite of that, and then we'll add 2. So let's go ahead and combine or distribute this negative and add like terms together. So we get negative a squared minus 2a minus 1 plus 2. Well, the minus 1 plus 2 there is going to turn into plus 1. So that's what g of a plus 1 looks like. Negative a squared minus 2a plus 1. So all we have to do over here is add that to this root b plus 1. Now, this root is root b, and then the plus 1 was on the outside. So now we have plus a negative a squared plus a negative 2a plus 1. Well, now we've got like terms here. We got this positive 1 and that positive 1, so we're going to rewrite this as root b minus a squared minus 2a plus 2. And that then is the solution that we're looking for in their example 2, part D. Example 3, okay, it says use the graph here to find f of 0, f of negative 2, f of 3, and the values of x such that f of x equals negative 3. So let's deal with these first, okay? So this is saying when your your input value of x is 0. So when x is 0, the question is, what's your output value? What's your y value, essentially, when x is 0? Well, the y value here would be that point right there. If we think about that point, is x is 0, y would be 1. And we've talked about, I showed you earlier, that we can sometimes write this as x comma f of x. Well, if x is 0, it's x 0 comma f of 0. Well, that would be x being 0, f of 0 would be that 1. So basically here what they're asking you is if x is 0, what's your y value? What's your y value that goes with that? In this case, it would be 1. Here, if f is negative 2, if we're looking at f of negative 2, okay, so our x value is negative 2, so I go to negative 2. What is the y value that is graphed here with negative 2? And that y value is negative 3. So f of negative 2, do it this way, f of 0 was 1, f of negative 2 is negative 3. And now if I find f of 3, okay, so that says that x value is 3. I'm going to go over to 3 on the x-axis, and I'm going to go up, and it looks like the y value that I get on that point right there would be 3. So f of 3 equals 3. And what's nice graphically is that these are ordered pairs. This is the, f of 0 equals 1 is x is 0, y is 1. This is x is negative 2, y is negative 3. And this one is saying x is 3, y is 3. So when they ask this question, they're basically saying, okay, what x value, what goes there that will produce a y value of negative 3? So I'm going to go look for my y values that are at negative 3. And those are my y values that are negative 3. And if we look at this, there's a couple different places that I have a point that has a y value of negative 3. There is a point that's going to have a y value of negative 3. So the x value that goes with that is 2. Okay? But if I look over here, that thing has a y value, that order pair has a y value of negative 3. So negative 2 and positive 2 would be x values that satisfy this requirement. Okay, and if you think about it, that's okay. It still meets the definition of a function in which every x value has one output. An x value of 2 has the one output of -3. So I'll plug in 2 as many times as I can. Or if I go look at 2 on this x axis, and I go look for the y value that goes with it, and if I do that over and over again multiple times, each time we'll come up with -3 being the y value that gets paired with 2. When I look at -2, the only y value that ever gets paired with it is -3. So based off this information, we still have a function here. Here it says how to determine if the given table of values is a function. And here what we're going to look at is that idea is that when I have an input, am I getting, for the same input, am I getting a different output? Okay, and that would violate being a function. Okay, so we're looking here. Maybe I'll write this way for you. And this will allow you to determine that it's not a function. It says for repeating inputs. Okay, so if I look at, I think, one of these examples. So here I've got repeating inputs here. Okay, do you ever get a different output? Okay, if that happens, then not a function. Okay. Okay, so if you have repeating inputs and you get a different output, it's not a function, because that says then for every input, remember the definition says for every input you get one and only one output. Okay, well if I violate that, then it's not a function. So that's kind of what we're looking at here. So here I've got inputs 2, 5, and 8, and they're all different. So that means to me my outputs, I don't really care. They're going, if whether these are all the same or they're different, it doesn't matter because these inputs were different. So this here is in fact a function. This one here is not a function because we're saying when I have the input of 1, so input of 1, it's giving me, if we go back to that mapping idea, it's pairing me up with an output of 0. So that's fine. But here now I've got 5 paired with 2. So 5 goes to 2. But in this one it says 5 pairs with 4. And that hopefully visually maybe opens your eyes to the idea that we've got an input that is giving us 2 different outputs. And if that happens, this thing is not a function. Okay, you violate the definition. So how do we deal with this maybe the best way in the graphical sense of things? And in every one of these things, this can be changed to a graph. This can be changed to a graph, and maybe I'll show you that here in a moment. But we use what we call the vertical line test. And what the vertical line test says basically is if I take that line right there and I just start sliding it through, okay, through my graph. I'm just going to put it right there. Right there we're seeing that, and actually let me go to a whole number, right there at -1. Right there at -1, we're seeing that our graph is intersecting this vertical line right there. And basically that says when x is -1, you are getting a y value back of what looks like maybe +3 there. And because it only intersects that vertical line one time, it tells me that when x is -1, you only get one output of 3. Okay? So at that stage right there, what we're doing is we're passing the definition of a function for that x value of -1. Okay? So for the input of -1, we get only one output of 3. Now, as I pass through everywhere else, that needs to be maintained. Okay? So when I have an input of -2, do I still only get one output? When I have an input of -1.7, do I still only have one output? So I drag this thing through the entire curve, and as long as at every single spot that I drag that through, every single x value produces one and only one y value, then that thing passes the vertical line test. Okay? So you pass, let me write this down for you. passing vertical line test equates to having a function, and the way you pass is that your vertical line intersects your graph only one time at all possible x values. Okay, so that's how we pass it. Then failing it would be kind of the converse of that, meaning that I intersect twice. All right, I guess maybe not the converse, but it just means that when I draw this thing through, when I draw that line through, if that line were ever to intersect the graph twice, we would fail, and it would not be a function. Okay, so this one here is a function. It passed the vertical line test, but when I get down to this one here, okay, and I draw this vertical line, okay, right there I pass. When 0 is the input value, I get an output value of 0. So right there I pass. But let me come out here and I start failing it in these other spots, and they all fail for the same reason. But let's look at maybe that one there, when my input value is 3. When my input value is 3, my x is 3, I get an output right there that looks like maybe 1.5. And down here, I get an output that looks like maybe, so when x is 3, my output is 1.5. But down here, when x is 3, my output is negative 1.5. So there we're getting the idea, if I go back to a mapping, we're getting when my input is 3, we're seeing that my output is either 1.5 or negative 1.5. Okay, so that input of 3 is now being paired with 2 outputs. This x value has 2 y values, and that means it's not a function. Okay, so we've failed the vertical line test because this vertical line here, and all these vertical lines except for that one, are intersecting our curve at 2 spots. Okay, and when you intersect at more than 1 spot, you fail the vertical line test. So failing it is when you intersect the curve more than 1 time at some particular spot, and all you need is 1 spot to do that. So you might have a curve that looks something like this. Let's say that my curve is that thing there. Okay, and if that was all I had, then it passes the vertical line test everywhere. But maybe for some reason there's a rule that's providing a point right there. Okay, so now as I drag this line through here, passing. Okay, maybe I jump to the other side, I'm passing all the way over here. So there's an infinite number of places that I pass. But right there, for whatever this x value is, let's say this x value, right, let's call it x sub 1. Whatever that x value is, I'm getting that y value back, and I'm getting that y value back. And that's a problem. That's an x value paired with 2 different y values. So to fail the vertical line test, you only need 1 place to fail. To pass it, you need to pass it everywhere. Okay? Failure 1 time is enough to say the whole thing is not a function. Down here it says how to determine if a function is an equation is a function. And really the best way I think to do this, if you're struggling, is to graph these things and then apply the vertical line test. So when I look at, and I'll talk about it a different way as well here in a moment, but when I look at that, y equals x squared, it's that curve right there, or it looks like that. And as I draw my vertical line through there, it's going to pass. When I look at y squared equals x, and it might actually be easier. That's going to, I was thinking about opening GeoGebra, but I don't have it. I'll take a minute to open it. That curve right there is going to look something like this. Okay, which that thing is now failing. If I put a vertical line right there, it fails. Okay, absolute value of y equals x. Going to be kind of a similar thing to that parabola. It actually looks like this. It's a V, but it's kind of opening to the right here. Again, we fail. Okay, and then this one here, y equals 3x plus 1. Well, that's 3x plus 1 would be up 3 over 1. So it's a linear idea, linear function, and that passes a vertical line test. So as we're going through here, anything that is polynomial, okay, and this is polynomial, is going to be a function. Okay, this passes the vertical line test, and because it's essentially it tells me that y can only be one type of number. Okay, when I solve this thing for y, it can only be one number. The reason this one fails is because, and it provides a parabola, but it's open in, to the right here. But the reason that fails is because if I do a little bit simple algebra, if I solve for y, I get y equal plus or minus square root of x. Well, that means y is equal to positive root x, and we have y is equal to negative root x. So that's telling you that for some x value, you could have two different y values. You could have a positive y value, and you can have a negative y value. So say this x is 4. For that 4, if I plug 4 in right here, it's going to say your y value is positive 2. So you get the order pair 4 comma 2. If I plug that 4 in right here, I get the opposite of the square root of 4, which is negative 2. So I get 4, negative 2. You get two different y values. Same thing happens here. Okay. Absolute value, obviously we get a positive and a negative, and we have an issue. Okay. Anything that is linear is going to pass the vertical line test, unless, I guess there's one situation that doesn't happen. So this is linear. It's going to pass the vertical line test. The only time that it would not pass and be a function is when I have a vertical line. And vertical lines are in the format of like x equals some number. Let's just call that number c. Let's say that c in this case would be 2. So if I had x equals 2, well, that line is going to look like that. Okay, it's still linear. But if I put in my vertical line and I start tracing through here, right there it fails, because there's a lot of different y values that get paired up with that too. So that would be a situation where you fail the vertical line test, and that is not a function. But every other line is a function. All right, and I think that's kind of the wraps for 3.1. I believe this stuff here is talking about 3.2. You may see in 3.1 they talk about domain and range at times, maybe with some vocabulary. Your input values, your x values, are what we're talking about as domain, just another word for it. And your output values are the range, just another word for it. Okay. And the way I always remember that is domain and range. Those are alphabetical. Okay. Input and output. Those letters are alphabetical. So domain is your input, range is your output, and also x and y. Domain is your x values, range is your y values, again alphabetical. Okay, so respectively, if you can remember those, when I say input, automatically know they're talking about my domain, because I and D respectively are alphabetical in comparison to range and output. So hopefully that maybe helps as you guys move through with the rest of the course. Again, I want to thank you guys for being great for the last several days. And again, if you ever have any questions or need my assistance, please don't hesitate to shoot me an email or ask me, and I can do what I can help where I can.